What's going on, guys? It's the Unhinged Engineer here, and today I am very excited to make more content about aerospace engineering, which you guys seem incredibly interested in, which is great for me because I love aerospace engineering, and that's what I do, it's what I studied, I love it. I mentioned in a previous video that despite popular belief, aerospace engineering is actually a really generalist degree. I think kind of the reputation it has is that it's super specific, and it is in certain ways, right? Aerospace is about a specific subset of industries that's relatively small, as opposed to a area of study, like a knowledge base that could be more broadly applied to, dozens of industries, right? And so in that way it's specialized, but overall the degree itself is pretty general. You learn a little bit about a lot of different things, and naturally that leads to lots of different opportunities for specialization in different areas depending on what you're interested in. And I think there's several pros and cons to kind of specialization early in your career, which I'd be more than happy to talk about in a separate video. But just to kind of give you guys the options, a lay of the land, I want to provide the 10 different types of aerospace engineering that I have seen throughout my education, my career, and the 10 different types of specializations you might find interesting if you decide to pursue this degree. So without further ado, let's just jump right into it. So first, I'm going to briefly touch on those different industries, right? I'll probably make a separate video about all the different industries that aerospace engineering can be applied to, but just to briefly kind of segment out the different industries in which you could work once you get out of school, I wanted to touch on that. We'll spend the majority of this video going through these kind of broad categories of job as I've seen them, right? Different kind of buckets that you can put people into, but then more specifically, like the actual job titles and kind of career tracks, positions, whatever you want to call it, that you'll see people actually hold, whether in internships or as full-time employees. And then after that, I'm kind of going to break down these categories, break down these buckets a little bit, and talk about some of the overlaps that might be not entirely obvious, but in my experience, if you can kind of live at the intersection of several fields, that's kind of the best place to be, because then you get to work with lots of different people, learn lots of different things, kind of assume more of a leadership role. I've really enjoyed trying to work at the intersection of different fields as much as possible, and I want to share, despite these categories, where they may actually overlap with each other more than you might think. So let's jump into the different industries, just to kind of enumerate them all. Like I said in the beginning here, as a field, aerospace engineering is concerned with a set of industries rather than an area of study. In my experience, and something I heard from my professors pretty early on, aerospace is unique from all the other ones with a couple of exceptions. There are a few engineering majors that don't really have like a core knowledge base that everything links back to. Rather, they focus on an industry and then they apply fundamentals or entry-level concepts of lots of different knowledge bases to those industries, right? And aerospace is like the prototypical example of that. So, like an obvious one is aeronautics, aircraft, boats. Like boats is a big one people don't think about because boats moving through water, that's moving through a fluid, aerodynamics, etc., etc. But aeronautics is a huge industry, of course. Astronautics, satellites, rockets, just like aerospace, that's space side. Obviously, that's an industry unto itself. Aviation, so instead of like the fighter jets and the aircraft carriers you can see there, just commercial aviation of like large passenger jets, cargo jets, large commercial aviation, that's an industry unto itself. And then, of course, no surprise, defense, working on missile systems, drone systems, other types of weapons and munition, etc., etc. So there are lots of different industries in which aerospace engineering can be applied, and these are the ones that come to people's mind, but in my opinion, there's lots of other ones that people don't actually think about that aerospace engineering can be applied to, right? And that's a subject for another video, but just overall, when you think aerospace engineering degrees and the kinds of jobs and industries in which people get those jobs, these are like the different buckets of industries. I'll go into more detail about it in another video. Okay, now let's talk about the real reason we're here, the different types of jobs that aerospace engineers can have, right? So you're starting an aerospace engineering degree. Once you get past through some of those gen eds, you're starting to sample different bits and pieces, the different knowledge bases like we'll talk about, and you're starting to think about what you want to specialize in. So the first kind of broad bucket I want to dump people into is what I'm calling dynamicists, which for the record, apparently autocorrect says dynamicist is not a word, but I've heard it used about 10,000 times. So I'm pretty sure it is a word, but feel free to correct me. Anyway, dynamicists. Dynamicists are people concerned with the motion of or external forces on, so emphasis on external here, a body or a system. Effectively, we're moving stuff according to some laws of physics. That can be projectile motion, so we launch something, obeys laws of gravity, stuff like that. Rotational motion, so maybe some satellite is spinning or slewing to point at different things, right? Fluid motion, like through an engine or over a wing, like an airfoil, stuff like that. These are all just people who are focused on effectively physics. These are very, very important competencies for different types of vehicles. Like the way a rocket moves is different from how a drone moves, is different from how an aircraft moves. Motion is a big deal. And so there's lots and lots of people whose job it is to really just understand these laws of physics and how they're used in the real world. So what are some examples? A classic one is aerodynamicists, so people who are concerned with wing design or control surfaces like flaps and rudder and things like that. Calculating the drag that a body might experience and different ways of mitigating that drag. Or maybe, if you're working on something like an F1 car, using that drag to your advantage through stuff like downforce. People concerned with fluid motion, most of the time that's air as far as we're concerned with aerodynamics, but also there's like maybe you want a boat to require less energy to cross a certain distance, so you need like a sleeker hull, you need less surface friction so that the water kind of parts ways around you more easily. So that would be fluid dynamics, but you get the idea. Now beyond that, let's say you get high enough that air isn't a problem anymore, astrodynamics. Now we're concerned with orbital mechanics, like two-body problem where you're just concerned with a satellite orbiting the Earth. You could have a three-body problem, or maybe you're doing some crazy, lunar transfer, trying to go explore the moon or Mars or something else. So that's like at the macro level. There's also like the micro level, orbital mechanics in terms of like relative navigation around other satellites or around a point on the Earth, stuff like that. And then beyond that, again, kind of getting back to that rotational piece, obviously the orientation at which a satellite is pointed or the slews between those different orientations are really, really important to its operation for stuff like collecting power with solar panels or communicating with the ground or stuff like that. It's actually an area I've spent like a large part of my career focused on. In any case, astrodynamics, same concept as aerodynamics, except you're concerned with, planetary bodies or satellites orbiting around those planetary bodies. And also I would throw like rockets in here. I think propulsion is kind of a separate thing, which I'll talk about. Obviously we're launching stuff into space, so you get into space in order to do that. That's astrodynamics. Okay. Last piece here, just kind of broad bucket, like system dynamics. And I'm using this to describe dynamics of vehicle types. So aero and astro are kind of more a function of the environment in which these vehicles are operating, but vehicles themselves inherently have weird dynamics that are all different and are worth knowing. So a drone, for example, changing the different propeller speeds to change its orientation, and then once it tilts, it starts to move forward because you get that net forward motion, like all the dynamics of how FPV drones work. Similarly, control surfaces on an aircraft, right? Like how you use flap versus rudder to land a plane or take off or whatever, do just about anything. Another great example would be for something like a rocket or a missile. You've probably heard of thrust vectoring before, where you're able to actuate your thruster in the back, and that changes your net thrust vector, which then changes how the thing moves. So all these idiosyncrasies of the vehicle's motion itself, like the platform, as we would call it, rather than just the environment of like, oh, I'm in space, I'm far enough out in space that I care about the moon and the Earth instead of just the Earth, or with aerodynamics, I'm in the water, I'm in the air, I'm this high, the densities, whatever. I'm just kind of using system dynamicists as a bucket for people who know a lot about the dynamics of specific vehicle types or platforms, we call them in the industry. Okay, next bucket here. Shouldn't really be a mystery. Structural engineers. So in certain schools, like I know at my alma mater, before I got there, they were separated into two departments, but originally aerospace and mechanical were actually part of the same department. Most of the students were mechanical engineering students, and then aero is kind of a subset of that. Eventually, a lot of departments get big enough that they break out. In any case, this is kind of like what you could refer to as aeromechanical engineering, which obviously these vehicles are very, very heavy. They're very complex. They're put through really difficult structural conditions during launch and exit into the atmosphere, which we'll talk about. And so there's lots of aeromechanical work to be done. So as you would imagine, these people are primarily concerned with the structural integrity of the vehicle, aka don't die, right? Like don't rip in two, don't kind of have these crazy shear forces that break solar panels or rip wings off. Similarly, if you're launching into space, don't shake so hard that you break all the components inside, stuff like that. People who are concerned about the structural integrity of the vehicle. Some examples of this are relatively straightforward. Just like general structural engineering, like that's definitely a job unto itself. People who look at different components of the vehicle structure and how they might bend or break or potentially interfere with one another. Similarly, I know for launching vehicles into space, vibration is a serious concern. Different oscillation frequencies and nodes of that oscillation could potentially break stuff. Honestly, I don't know much about vibration. I just know it's important. Yeah, you get the idea. Beyond that, thermal engineering, people who are concerned with heat transfer. And if these things get hot enough, whether due to drag in the atmosphere from the outside or heat from the components like computers or whatever, kind of radiating off. Solar panels generate a lot of heat when they're collecting power. Batteries are inefficient, so they let off heat. Whether it's internal components letting off heat or kind of external environmental factors imparting heat on the vehicle, if things get too hot, they start to melt and then they start to break. And that's obviously not what we want. So people making sure that everything's kosher and that the vehicle can withstand the energy being imparted into it. Those are thermal engineers. And then lastly, propulsion here. Rocket engines are incredibly complicated. I'm primarily focusing on like rocket engines here because a lot of times, let's say you're working on a propeller plane. A lot of times people who are working on those propellers in the front are more dynamicists, like from the previous example. But rocket engines specifically, I'm talking here, are a very unique thing because they're what would be called aerothermoelastic structures. It's effectively saying stuff gets really hot, which breaks stuff and changes how fluid flows through it, which then makes things really hot and then breaks stuff. They're all coupled. Physical coupling is a core principle of designing safe and effective propulsion systems. And so propulsion is just this like black box magic unto itself. A lot of people get advanced degrees in it, like master's degrees and PhDs. It's very complicated and it's very niche. Also very cool, and I've heard lucrative as well. Last one here, material science, which again is kind of like that mechanical or maybe even like chemistry part of how do we design these systems. Carbon fiber behaves differently under tension versus compression versus different heat profiles as compared to something like aluminum or mylar or whatever else. The materials themselves all have different properties that have to be accounted for in the design of the vehicle, and these people focus on that aspect of it. So yeah, okay, structural bucket, pretty broad, a lot of cool stuff. Last piece here I want to talk about is the one I've lived in primarily, which is software. So software, it's like straightforward. It's people who write software, duh. In the modern world, the way we design and operate aerospace vehicles, a lot of times we can't do that without software. There's lots of different types of software that people could work on. An obvious example is like flight software. Most aerospace vehicles, be it satellites or aircraft or drones or whatnot, have different compute platforms on them, whether there's something complicated like a full like computer with a carrier board and all the I/O, or something dumb like a little microcontroller like a PX4 flight controller you may have heard of before on FPV drones. Regardless, the code that runs on the vehicle itself, that's flight software, and the people who write that code are flight software engineers. Lots of really interesting, not only aerospace principles to that, but also traditional CS principles surrounding like memory safety and performance optimization, stuff like that. Really cool field. The next one, guidance, navigation, and control. Obviously, GNC code runs on the aerospace vehicle, but GNC is specifically focused on these three functions of the vehicle, which is guidance. So how do I get around the environment in which I'm operating? And if I'm trying to achieve some goal, whether it's get somewhere or see something or whatever, how do I do that? That's guidance. Navigation is how do I know where I am, right? So I'm taking different sensor readings in and I get some like loose operating picture of where I'm at, but that's noisy, and there's considerations of how you synthesize different sensor modalities into a fundamental picture of where you are. That's all navigation. And then controls, right? So if I know where I am and I know where I'm trying to go, what do I physically need to do to get there, to close that delta? You can see here I have a PID controller as a classic example. What do I need to change about my physical state, whether it's my control surfaces or the thrust I'm letting out, stuff like that, to actually get to where I'm trying to go as determined by my guidance system. So GNC, super broad field, very cool. I've worked in it before a lot. Avionics then is focused more so on those sensors. Like just as an example, satellites have lots of different sensors. Some are optical, some are electromechanical. Similarly, they have different actuators like reaction wheels and thrusters oriented in different ways. Magnetorquers you may have heard of. There's lots of different sensors and actuators on the spacecraft that allow it to do its job and to obey those kind of GNC algorithms we just discussed. Satellites are one example, but they're present on just about every aerospace vehicle, and avionics focuses on those specifically. There's actually a lot of electrical work associated with that. And then lastly, modeling and simulation. All these things, we have to simulate how they work, like to get a better understanding of whether our requirements are closing, whether our vehicle is behaving the way that we want it to. And so we need a lot of code to model and simulate those things. Now, I'm putting modeling and simulation here. You'll notice a lot of what I talked about previously with structural and with dynamics involves simulation, but modeling and simulation engineers write the code to do that stuff. So in a lot of ways, they're building the tools that enable other aerospace engineers or different types of engineers to do their job. That's what a modeling and simulation engineer does. It's pretty cool. Last piece here, I want to talk about overlaps between these categories. So I'm sure at some point throughout that whole spiel, you were like, wait, doesn't that one belong in that bucket? Like, that doesn't make sense to me. The answer is you're probably right. Like, these are very ambiguously defined buckets, just as I see them in my personal anecdotal experience. But as I'm sure you can understand by now, there's lots of different overlaps and different subsections that you could put in one bucket versus the other. And I want to talk about that. Okay, so I have like a crazy 3-way Venn diagram here to kind of demonstrate these overlaps as I see them. Top left is going to be dynamics, the red one. Bottom is going to be software in blue, and then top right is going to be structural in green. Just as an easy visual way to lay out the different buckets, and more importantly for this part of the video, the overlaps between them. So I want to go around this in like counterclockwise order, just to provide some reason to it. So let's start off with dynamics in the top left, right? Aero and astrodynamics, as I said in the very beginning, those are obviously firmly dynamics fields, duh. Beyond that, I would say GNC and mod and sim are kind of fields that involve knowledge of whatever dynamics you're trying to simulate or you're trying to design algorithms to take advantage of. But also there's a strong software component to those, whether you're GNC and you're writing like code that's going to fly, or you're building software tools that other people are going to use. There's a lot of software involved with that, obviously. So that's kind of an overlap between the two that immediately jumps out to me. In terms of squarely software, I would put avionics and flight software. One thing I will note is like avionics does have an electrical piece to it. So like that's not all necessarily writing code. Sometimes that's writing firmware or reading off voltages and verifying that sensors are not going to fry up in space or in the sky or whatever. But nonetheless, it's about systems that primarily contribute to the vehicle, either in terms of data, right? So sensors are providing data, or based on commands, which are usually software commands, changing the physical conditions of the vehicle. I don't have any overlap here between structural and software. I mean, that makes natural sense to me. One's concerned with the digital world, the other one's with the physical world. Obviously, there's certain aspects of software that do kind of overlap, but nonetheless, I think for the most part, it's fair to say that structures are their own thing, and there's a lot of really cool stuff within structures, like the vibe stuff we talked about in the beginning, thermals and heat transfer, stuff like that, the material science, what you actually construct the vehicle out of, et cetera, et cetera. The one thing I will say overlaps, though, is between structural and dynamics, and specifically propulsion here. So obviously, and things I focused on originally were the structural integrity of the rocket itself, whether it's the rocket nozzle or the compressor or heat coming out of that chamber and affecting all the structures of the engine itself. That's what I was focused on specifically in terms of propulsion, but also we're trying to get somewhere. And so how our propulsion affects the vehicle matters a lot. So that could be a function of like the flow rate of how much exhaust, how much fuel is coming out the back. If you're doing something like thrust vectoring, suddenly that changes, how much forward motion you get versus off kilter motion, which could be intentional or unintentional. Propulsion, I would say, kind of lives at the intersection between dynamics and structural piece, which is because when it's in the engine itself is kind of a static thing, but then once you kick it out the back, now you're concerned with the motion of the vehicle that you've caused. That's the whole purpose of propulsion. And then the last thing I want to talk about, I actually didn't mention this previously. The thing that uses all of them is like testing and systems. Testing engineering jobs and systems engineers themselves can sometimes get a bad rap as just kind of being like administrative. But to their credit, and this is as someone who has worked as a systems engineer before and conducted tests before, you need to know about just about all of these things, assuming that the tests you're doing, if they're vehicle level tests, are using all these systems, which if, again, you're testing the entire vehicle, probably is. Don't sleep on systems engineers. They do know a little bit about a lot of things. And I do think like for the purposes of designing an aerospace vehicle and coming up with requirements and then tests that kind of validate those requirements, that requires knowledge of just about everything to do with the vehicle, which again is pretty cool. So yeah, okay, this was a bit of a ramble video. I just kind of went and listed off all the different types of aerospace engineers, but to be honest, I've seen a lot of buzz around my previous videos to do with aerospace engineering, and one of the things that was most intimidating to me when I got started was what the hell do I specialize in? I'm interested in lots of different things. I'm not interested in other things, right? You take a bunch of classes, you drink from the fire hose, and some of it you like, others you won't. And at least to me in the beginning, it wasn't clear how these different fields are kind of cordoned off. And if you're trying to, ensure that your chances of getting a job are as high as possible, maybe you want to focus in on one or a couple of them because that's what you really like and feel like you're really good at. So yeah, I make videos about professional success. I think knowing what you're interested in, focusing on those and building up those strengths is a really, really core part of success. I know it has been for me. And so if you're interested in professional development content, like what you saw today, then definitely like, comment, subscribe to the channel. Like I said in the beginning, I'm the Unhinged Engineer. Stay tuned for more aerospace engineering content among the other things we talk about on this channel. And yeah, thanks a lot for watching. I will see you next time.